Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. Find the longest equal subarray. The problem is very interesting application of binary search two pointers. If you haven't solved this problem yet, I would strongly encourage you to pause it right away and give it a try. If you have solved it but haven't thought of binary search or two pointers while solving, you can think for a moment before continuing. As always, we will start from scratch. We will look at the very brute force solution and see how to think and how we can optimize it to n log n solution and finally to order n solution. All the timestamps will be there in the description down below. So if you are interested in only specific section, feel free to jump back and forth. So with that, let's get started. The problem states that you are given a zero indexed array nums and a integer k. A subarray is called equal if all of its elements are equal. We have to return the length of longest possible equal subarray after deleting at most k elements. And subarray definition we all know. So let's look at one example. We are given this array and k is 3. Basically, we can delete at most 3 elements, and after deleting 3 elements, we need to return what is the size of the longest possible equal subarray. So what they are saying is we will delete 3 elements, we will delete 2 elements, one at index 2 and second at index 4. And if you delete this 2 and this 1, the array would become 1 3 3 3. So this is a new array, and here we can see there is a continuous subarray of size 3 in which all the elements are equal, or in other words the subarray is equal, and hence 3 is one possible answer. You can try out any other possible combination. Basically, you can try deleting any other numbers. You will not be able to make a equal subarray of size greater than 3, and hence 3 is the answer. So hope the problem statement is clear. Now how to solve this? So let's assume that this is our subarray, right? Now what can happen? We need to find out the longest equal subarray after deleting k elements. So our subarray can start from here, or it can start from here, or it can start from here, and so on and so forth, right? Now for each of these starting point, if we are saying that our subarray is starting from here, we know that the entire subarray must contain 2, because that's what the definition of an equal subarray is, right? The subarray should contain all the elements that are equal. So if we are saying that our subarray is starting from this index, all the elements that we will be choosing in this subarray should be equals to 2 itself. So what we now need to do? We now need to find out what is the maximum R that is possible. And how we will find out maximum R? Basically, for each L, we know that we are only interested in 2's. So whatever element we will encounter that are not equals to 2, we have to delete them. There is no other choice, right? So we will keep on doing this until we reach a point where we can't delete any more elements. Basically, we have deleted k elements already, and the moment we reach that particular R, we will just count how many 2's we encountered, and that will be the length of the longest equal subarray starting from this particular index. We will do this for all possible starting index, and we'll take the maximum across all of them, and that will be the result, right? Now just to reiterate this part, that for this L we need to find out how many what is the largest possible R there. So let's assume that k is 3. So if k is 3, you can start your R with this. So because L and R are equal, like you don't have to delete anything, you increase your R. Because your L has 2, everything has to be 2. So you have to delete this element. So basically you deleted one element now, So let's say you deleted this. Now you increased your R, you got 2, so 2 is fine, you don't need to delete this. You increase your R, you got 4, again 4 you have to delete it, right, because 4 is not there. You want everything to be equals to 2. Now you increase R 2, that's fine. You increase R 1, you have to delete this. Now again 1, you have to delete this, but you have already deleted 3 elements and k is 3, so basically you can't delete any more element, and hence this is the maximum possible R for this particular L. And how many 2's you encountered during this journey? 1, 2, 3, and hence for this L, or if for a subarray that starts at index 0, the maximum possible equal subarray length can be 3. You will do this for all possible L and take the maximum, and that will be your result. Now what is the time complexity of this entire solution? Basically for each L you are traversing your R rightwards until you hit k elements. So in worst case k will be equals to n, and in worst case the complexity would become order n for a single L, and you will have to do this for all the L's, and hence order n square, right? Now order n square will surely not pass given the given the value of n is 10 to the power 5. We need to optimize this. Now how to optimize this? There are two ways again, like there are two n's, right? First n comes from the fact that we are iterating over all the L's, and second n comes from the fact that for a single L we have to iterate over all the elements one by one to figure out what is the best possible R. Which of these two n is easier to remove? So if you don't iterate over all the L's, it means you are saying that I will not try every possible starting point of subarray and still figure out the best subarray. That is harder than actually removing, actually optimizing the fact that somehow we will see if we are able to find R in less than order n time. So let's do that. The problem now is we have to find this R in less than order n time. Now notice that previously we were iterating over all the elements, but does it even matter if we are able to reach our R here? Answer is no, because at the end what matters is how many 2's you have taken in your final array. So what you need to know is, can your R ends here? Can your R ends here? Can your R reach here? That's the only thing you are interested about. You don't need to know whether your R can reach here or here, because even if it reach here, the number of 2's that will be there in your final equal subarray would remain same, irrespective of whether your R reach here, here or here, right? So now a simple optimization that you can do is you will only check R's at equal indexes. So if you are checking for the value 2, you will only check the R's where value is equals to 2. So in this particular case you will check this thing, you will say okay, can my R reach here? And how you will answer that? You will say okay, from L to R there are 3 elements, and I know that I have encountered 2 2's, so number of non-2 element is 1, and 1 is less than 3, and hence my R can reach here. The same fashion you will say okay, can my R reach here? Again you know that there are 5 elements here, and among the 5 elements you have 3 2's, right? So there are total 2 elements that you need to delete, and k is still greater than 2, and hence your R can reach here. Now can your R reach here? You know that there are 8 elements here. Among 8 you know that there are 4 2's. Now if there are 4 2's, it means there are 4 non-2's. It means you have to delete these 4 elements. Now but k is 3, so you can't delete these 4 elements, so basically your R can't reach here. So in other words, the maximum length of your equal subarray starting at this index would be 3, right? Now this is surely better than what we were doing previously. Previously we were iterating over all the indexes. This is better, But in worst case, what can happen is each of the element is 2 itself. So in that case, you will have to iterate over all the indexes again. So it is, in worst case, it is still order n. But this gives a very interesting factor, a very interesting point, that we only need to care about the indexes of a particular element. So let's say if we are checking for 2, then we only care about what are the indexes where 2 is present. So we only care about 0, 2, 4 and 7. So we know that 2 is present at these 4 indexes, and hence we only care about these indexes. We don't care about any other index. Now if we are starting from here, we just need to find out what is the maximum R that is allowed. So what we are saying is this R allowed, the allowed true or false is something we will calculate via this. We know that from this L to this R there are 3 elements. How? Like it is an index 2, it is an index 2, index 0. So how many elements are there in between? 3 elements. Now among 3 elements, 2 are 2s. Why 2? Because we R minus L is 2. So there are two elements which are equals to 2, and hence there is one non-2 element. You have to delete one non-2 element, which is this in this particular case, and if the k is greater than that, you can delete this. So exactly same thing, it's just that the array is now reduced with, we only care about the indexes of the 2s. Now think about this, you are iterating over R. Can you do a binary search instead of linear search? The answer is yes. How? Let's think about it. So we have already recorded a binary search video. If you are new to binary search, you can watch that. But in general, the approach is, let's say you have a search space of n. In this particular case, you have search space of 4. You divide your search space into half. Now let's say you are at index x, or you divide the search space at index x. Now if you are able to say that, or if you are able to deterministically say that I can skip either the left or the right half, then binary search is applicable here. Now in this particular case, let's say R is equals to x. Now at any given R, you can answer whether this R is possible or not with this simple trick, right? You can simply do array R minus array L minus R minus L, and whatever value you will get, you will check whether it is less than equals to k or not. If it is, R is possible, otherwise R is not possible. Now if R is possible, then does it make sense to search in the left half at all? The answer is no. Because you know that from this L you are able to reach this particular R. So this in turn implies that all of these R are valid, and you want the maximum R that is possible. So you will not search in the left half at all. Instead you will only search in the right half, right? Let's take opposite case. Let's say the R that you are talking about is not reachable. Like the value, if you evaluate your function at x, the value is false. In that case, what it means is, from this L you can't reach this x. If you can't reach this x, it is sure that you will not be able to reach x plus 1 or x plus 2 or anything after that. So in that case, it doesn't make sense to search in the right half. You can only search in the left half, and that should be it, right? So we can see here binary search is applicable. We are able to deterministically say whether to go left or right based on a particular function, and because of that we can simply do a binary search for R and figure out what is the best possible R for a single L. And if you remember, we had 2n, the second n is now reduced to log n because of binary search, and the complexity of n log n will pass the given time constraint. Let's quickly look at the pseudo code before we look into the order n solution. So the pseudo code would look something like this. As we have discussed, we will first calculate this array, because doing binary search over this array is bit difficult. So we calculated this index array where a particular element would denote what are the indexes where it is present, right? Now for each element, you know what are these indexes, right? So what you can do, either you can start your L from here and then go here and see. If you are starting your L from here, you will first go to the 2 index array, and then if you go here, you will then go to the index array of 4, right, and so on and so forth. So instead of doing this, what you can instead do, you can say, okay, I will try out every possible L for 2 at once. So that's just a way to optimize the value for this, optimize the implementation. So basically we will start with L, and whatever the element is, we will take all the L's for that element at once. So basically we will take this L, this L, this L, and this L at once. So that's what we have done in the implementation. We simply take the element, we take all its indexes, now we try all those L's at once. Now for all those L's, we simply do, like, this is the linear search that we were doing previously. We can simply replace this with binary search and we will get the answer, right? And notice this was the function that we are talking about. Basically we need to know how many elements we have deleted, and for that we can simply figure out how many element exist in between these 2 elements and how many element is equals to the current element. So how many elements are equals to current element is something we will get by just doing r minus l, and how many elements exist is something we will get by doing array r minus array l, right? So this is in this fashion you will be able to convert this this loop into logN by doing binary search, and overall the complexity would be n logN of this solution. So if you are new to binary search, or even if you know binary search in advance, I would encourage you to implement this solution as well, because that will help you understand the problem a bit better. Now that we know about binary search, I'm not showing the code for binary search because that would be straightforward. If you face difficulty, you can post and I can paste the code in the comment section below. Now whenever you are doing a binary search, more often than not you can do a linear search as well with 2 pointers. How? It depends on what the problem property is, but in this case it is applicable. So the simplest way to look at if 2 pointers are applicable or not is, let's say for this L you got this R, right, to be valid by just doing a linear search, right? Now what will be the value for this L? Is the value, or can the value be smaller than the R that we got for the previous element? If the answer is no, then you can apply 2 pointers, right? So in this particular problem the answer is no. Why? Let's say for this L you got this R. It means if you are starting from this L, you can delete enough element to reach this particular R without deleting more than k elements, right? Now if you are incrementing your L, it means number of element between R and L decreases, right? And if number of element between R and L decreases, you know that you will be able to delete exactly or even less number of elements in some cases than k and still reach this R. So for this L as well, this up till this R you are sure that you will be able to reach. So for this L, what you need to do, you just need to check for other R's. So basically you are not resetting your R to L, instead you are keeping your R at the point where it was previously and moving it forward one by one. So R will be moving in one direction and L is also moving in one direction. So in worst case you will be iterating over the array twice, and hence the complexity would be 2n instead of order n square, and for each L you will be able to compute R by this logic. So with this we can simply optimize our binary search for R with a 2-pointer application and get rid of logN as well, and the complexity would then become order n. So let's just look at one last example to make this entire thing a bit more clear. Let's say this is the array and k is 3, right? Now this, as we have discussed, we will build the indexes or the indexes array for each of the values. So we build the indexes array for 2, we build the indexes array for 4 and 1. So 4 is present at 1, 2 and 9. 1, this is not 2, this is 3. 4 is present at 1, 3 and 9, and 1 is present at 5, 6 and 8. Now once we build this array, for each L we need to find out the R. Now let's look at the 2-pointer approach. So for this L you are at this R, right? Now is this R applicable, or is this R reachable for this from this L? The answer is yes, because number of elements you have to delete is 0 here, right? Now let's increment our R. Is this R reachable from this L? The answer is again yes, because number of elements you need to delete is 1. How? It is at 3. So basically there are 3 elements between L and R. 2 minus 0 plus 1. There are 3 elements between L and R. And among 3 elements, 2 are 2's. How 2? Because R minus L plus 1 is 2. So 2's are 2. 2 are 2's. And hence there is just one element which is not equals to 2, and hence you need to delete one element. And 1 is less than equals to 3, and hence this R is applicable. Now is this R applicable? Again the same trick. Number of elements between L and R is 5. 4 minus 0 plus 1. Right? So number of elements between L and R is 5. 4 minus 0 plus 1. And number of elements which is equals to 2 is R minus L plus 1, which is 3. So 5 minus 3. There are 2 elements which are not equals to 2. And 2 is less than equals to 3. And hence we can delete these 2 elements. And this R is also possible. Is this R possible? Let's see. Again there are 8 elements between, right? And among 8, 4 are 2. So we have to delete 4 elements, but k is only 3. So this R is not possible. So for this L, this is the maximum R you can get, and because of this, the maximum equal array length currently is 3. Right? Now let's increment our L. For this L, as we have discussed previously, this R will be there. Like this is the R can be greater than this, but can never be less than this, right? So we'll keep R here. Now we'll just check, is this R possible now? The answer will be yes, because there are now 6 elements here. 7 minus 2 plus 1, there are 6 elements here, and among 6 elements there are 3 elements which are equals to 2. So 6 minus 3 would be 3, and k is 3. So we can delete these 3 elements easily, and this R will be possible. Now there are no more indexes afterwards, so number of equal array length that you can get by starting with this particular L is again 3, and maximum of 3 and 3 is 3. Now if you try with this L, again there is no R possible at all afterwards, so you will get 2. If you try with this L, you will get 1. So this is what you have get, like 3 is the maximum equal array length that you have got if the array has value 2, or if all the elements in that equal array has value 2. Now let's do the same for 4. If you do the same for 4, you will see for this L, this is the maximum R possible, because for this R there are 9 elements in between, and among 9 only 3 are equals to 4, and hence you have to delete 6 elements, but k is only 3, you can't delete 6 elements. So for this L, this is the maximum R, and for this L, this will be the maximum R in best case. So hence like even this is not possible. I think only this is possible. So from 4 you will get a maximum length of 2, right? And similarly from 1 you will get a maximum length of 3, and you will just take the maximum across all of them, and maximum across all of them is 3. So the answer for this particular problem is 3. Overall complexity is order n, because we are just building this, and then for each of the array we are doing a linear iteration of L and R using 2 pointers. So if you have watched till this point, I would strongly encourage you to pause and try to code both binary search as well as two-pointer approach by yourself, because until you code it yourself, you will not be able to retain, or you will not be able to understand if you have understood everything that is involved in the problem. So next we're looking at the code. The code is very straightforward. We first built this indexed array as we have discussed. Now for each of these array, we are simply doing a two-pointer approach. So we started our L with 0 and R is initially 0. Now we are checking whether R plus 1 is valid or not. And how we are checking that? As we have discussed, we will just check the number of elements in between. Number of elements between array R plus 1 minus array L. It will be plus 1 as well. And then we will check how many R equals. So R plus 1 minus L, there will be plus 1 as well. So because there are two plus 1s, I just removed these plus 1s from here. So this is the number of elements that you need to delete. And if this is less than equals to k, then this R is possible. You will just simply increment your R. And once you reach the maximum R that you can get, you will simply do the result equals to max of result comma R minus L plus 1, because this is the length of the longest equal array that you can get if you start with this particular L. And you will simply increment your L, and notice we are not doing anything with R, so R still stays at the position it was there previously, and hence this entire loop will just take order n time to execute in worst case. And we like this n over all the indexes will be equals to the size of the array, because these are subsets of the original array itself. So if you sum them all up, this will be equals to the size of the original array. So basically, to find out the R for everything here, you will take order n1 time. Find out R for everything here, you will get order n2 time. You will take order n3 time. So total complexity would be n1 plus n2 plus n3, which is equals to n. So overall complexity is equals to n. So hope you got the solution. If you have any doubts in any of the piece, feel free to post them in the comment section below. I would have an answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.